Another way to solve differential equations is with the Laplace transform. Initially, we're going to solve some equations we've already been solving, and you might say, why are we learning another method to solve the same thing? But you'll find as we go along that it also applies to some special functions of engineering, physics, and other sciences. And so then you'll say, okay, this solves some new problems too. But a lot of people in these sciences like to learn how to use it to solve the ones we've already been doing too. So we'll do those too. Now, I'm going to skip through some fun stuff at the beginning of the chapter. You can read if you want. Just say, here's what the Laplace transform does. If you give me a function f of t defined on 0 to infinity, again, we're thinking of the engineer's thing. You turn on the circuit at time t equals 0, and then it runs for all time and eternity. What does it do? So we're only interested in solutions starting at time t equals 0 and going out to infinity. Suppose I give you a function f of t. The Laplace transform is the integral from 0 to infinity of e to the minus st f of t dt. That gives you out a function of s, right? Because there's an s in here. T goes away because it's the dummy variable. It's evaluated at 0 to infinity. It goes away. And you get out a function of s. So the Laplace transform is like a black box. You throw in a function of t, and you get out another function of s. Turns out that actually s is a complex variable and f is a complex valued function. We aren't going to worry so much about that in here, because it turns out, that's for advanced mathematics, that if s, or if you put in, if you take a real value of s, then the Laplace transform f of s is real value, and so we'll only worry about the real values. Here's some basic Laplace transforms that are to be memorized that come out of this formula. If you put in 0 to the black box, what happens? Well, you integrate 0, you get out 0. So the Laplace transform of 0 is 0. Here's another one. Suppose I put 1 into the black box. Oops. Integral of 1 e to the minus st. Well, let's see. Integral of e to the minus st is e to the minus st over minus s. I plug in infinity and I plug in 0 and I take the difference. And I just get back 1 over s. In fact, I've got the derivation down here. Laplace transform of 0 is 0. Laplace transform of 1, you do this integral. Integral e to the minus st of 1 dt. And you get e to the minus st over minus s. Plug in infinity and you get nothing because e to the minus infinity is 0. And then subtract the bottom end point. 1 over minus s, right, you're plugging in t equals 0. 1 over minus, when you plug in 0, you get e to the 0 is 1. Over minus s gives you 1 over minus s, and you're subtracting that gives you 1 over s. I can take the Laplace transform of t, right? L of t gives me integral of e to the minus st times t dt. You can use integration by parts on this, right? You can set u equal t and dv equal e to the minus st dt, and you get uv minus integral v du. And evaluate each at 0 to infinity. And let's see, we plug in infinity here, and e to the minus infinity gives 0. But we plug in 0, we get 0 times this. All this comes to nothing, right? T equals 0 drops the bottom end point. T equals infinity. This part makes this part equal to 0, so you get nothing from this. So we just have to evaluate this integral at 0 to infinity. Well, let's see. This one's easy. The minus s is a constant and comes out. And then I integrate e to the minus st, and I get, again, e to the minus st over minus s. And so I guess I combined these here. So this one gives this, and this one gives this. And then I plug in 0 to infinity, and this one falls out, as we said. And this one at infinity gives 0, because the e to the minus infinity is 0. But at 0, you get minus e to the 0 is 1 over s squared. That one's subtracted, and you wind up with 1 over s squared. So when I take the Laplace transform of t, by integration by parts, here's its antiderivative. I plug in infinity and 0, and I just come out with 1 over s squared. And you can do this for lots of other functions. If you do n integration by parts, the integral from 0 to infinity of t to the n e to the minus st goes through all these gyrations. Comes out to be n factorial over s to the n plus 1. Aha, there's a formula for the Laplace transform of t to the n, just like there's a formula for the derivative of t to the n. It is Laplace transform of t to the n is n factorial over s to the n plus 1. Now you can take the Laplace transform of any power of t. How about that? Here's another one. If I take the Laplace transform of e to the at, that means you take e to the minus st times e to the at, right? The Laplace transform just integrates from 0 to infinity, e to the minus st times whatever function you put in, right? Throw into the black box. So I have to integrate this. Now these exponentials combine, I get e to the a minus st dt integrated from 0 to infinity. This is an easy one, right? E to the constant times t is e to the constant times t over the constant. A and s are just constants within the integration, right? You're holding s constant. And now you have evaluated infinity. Well, as t goes to infinity, as long as s is greater than a, this is e to a negative exponent times t, and you get 0. So the top endpoints contribute nothing, as long as s is greater than a. And then you divide, and then at t equals 0, you get e to the 0 is 1 over a minus s. Subtracted gives 1 over s minus a. So the Laplace transform of e to the at is 1 over s minus a. The Laplace transform of t to the n is n factorial over s to the n plus 1. The Laplace transform of 1 actually is a special case of t to the n is 1 over s. Laplace transform of 0 is 0. And you can also do sine and cosine. I'll let you look at these integrations if you want. It's not so important that you be able to do any of them. Just remember what the Laplace transform is. It's a black box. You throw in a function of t. You get out another function of s. For our applications, we'll just treat this as a real function. And the function f of s is the integral from 0 to infinity of e to the minus st f of t dt. It's that integral. And you get tired of doing those integrals after a while, so you memorize some of the ones that come up a lot. Here's some of the ones we did, right? So you memorize those. And then also, integral, or the Laplace transform of sine b times t, where b is a constant, is b over s squared plus b squared. Laplace transform of cosine bt, you can see the proof in the notes, is s over s squared plus b squared. So there's the most common ones. I say you should memorize these because it will really help you to do the problems quickly and to recognize when something is the Laplace transform of something. These come up all the time in lots of applications. The other ones, there's big tables of these, just like there's big tables of other integrals. But what you do when you need those, you go look them up on the table. These are the ones you have to know. If you don't memorize all these, then you can kind of figure them out as you go on a lot of the problems. But I'll recommend memorizing those. All right. What are some properties of the Laplace transform? Today we'll just introduce the Laplace transform. I won't use it to solve differential equations yet. But you'll see some of these properties later on. We'll need these. So a function is said to be piecewise continuous, maybe you've seen this before, on an interval I of real numbers on which it's defined. If it's continuous everywhere except at a finite number of points, let's call them tk, k equals 1 to n. So maybe it's not continuous at n points along the way in the interval I, that's an I, at which the limit from both sides has to exist. So you might have something like this. Here's a function that's continuous on this interval, it's continuous on this interval, continuous on this one. Single stroke of a pen is the intuitive concept. But there's a jump discontinuity here, right? The limit exists from both sides, but there's a jump. We disallow functions that go off to infinity or minus infinity. Those are not piecewise continuous. Piecewise continuous means where there's a discontinuity, there's at most a finite jump. Here's another one, the jump discontinuity. You can also have a hole here where there's a point where definition jumps up here and back down. We call it a removable discontinuity because you just fill in the hole, it's continuous. So removable discontinuities and these jump discontinuities are what we allow some-valued function then, when will it have a Laplace transform? We all know there's some integrals that don't exist, right? How do we know this exists? Well, we'll talk about these kinds of functions. That f of t is of exponential order if its absolute value is less than or equal to an exponential function, the famous meat function, right? m e to the at for some constants m and a. If f of t in absolute value is less than or equal to a constant times an exponential function, for t greater than some value at least, doesn't have to be near zero, then we'll say it's of exponential order. So it looks like this. Y equals f of t is bounded by some meat function, right? It's just a constant times a growing exponential. All right. Now here's the theorem using those things. If a function f of t is piecewise continuous on every finite interval from 0 to a, some a, and it's of exponential order, bounded by an m e to the at function, then the Laplace transform exists, at least for s bigger in its real part than a, the function in the exponential is bounding it. The constant in the exponential is bounding it. So there's a nice thing. All you have to do is get a function that doesn't grow faster than exponentially. Remember, exponential growth is very fast. So this isn't too big a restriction for a lot of real applications. And so if it just doesn't have more than a finite number of these jump discontinuities or removable discontinuities, it doesn't grow faster than exponential, it has a Laplace transform, so that's nice to know. And then it has this nice property of linearity. If two functions f of t and g of t both have Laplace transforms, so does a constant times one plus a constant times another. The Laplace transform of these, which is the function of s, is, if I have alpha f of t plus beta g of t, where alpha and beta are just numbers, the Laplace transform of the linear combination is the linear combination of Laplace transform. It's alpha Laplace transform of f plus beta times the Laplace transform of g. I'm introducing this notation here for brevity, right? The idea is it gets hard to write down this. Where is it? Way up here. L of f of t notation, the Laplace transform L of f of s. Instead, we'll write f of s, capital F, is the Laplace transform, or we'll write L of f or L of f of s, and those will all mean the Laplace transform. So when I take the Laplace transform L of a function, alpha f plus beta g is a function of s, I can calculate as alpha times the Laplace transform of the other plus beta times the Laplace transform of the other. Use the L over here and the other notation over here is what I'm doing. So here's the proof. The proof is really just the fact that L is an integral. If you take an integral e to the minus st times this, well, there it is. There's the Laplace transform's definition. The integral of the sum is the sum of the integrals, and you can pull the constants out. And so that's all this is. This is just a statement that the integral of the sum is the sum of the integrals, and you can pull constants out. Gives you this linearity theorem that we call it. This is very important if you have a Laplace transform of things that aren't in the table, whether they're constant times something in the table plus constant times something else in the table, you can still use the table to evaluate it, right? So here's an example. What's the Laplace transform of 4t squared plus e to the minus t? I don't know, it's not in the table. But the Laplace transform of this linear combination is the linear combination of transforms, right? It's 4 times the Laplace transform of t squared plus the Laplace transform of e to the minus t. And each of these are in the table, right? Laplace transform of t squared, may you remember, right? T to the n has transformed n factorial over t s to the n plus 1. So t squared has transformed 2 factorial over t to the 2 plus 1. Remember the Laplace transform of e to the at, where a here is minus 1, is 1 over s minus a. There we go. So we're getting pretty good at these already. And now we can simplify this with algebra. The Laplace transform is 8 over s squared plus 1 over s plus 1. The Laplace transform of this function of t, 4t squared plus e to the minus t, is this function of s, 8 over s squared plus 1 over s plus 1. Here's another one. Boy, sinh isn't in the table, hyperbolic sine. How can I take the Laplace transform of the hyperbolic sine? I rewrite it as its definition. Remember, hyperbolic sine is defined to be e to the t plus minus e to the minus t over 2. I write it like that and recognize, wait a minute, this is 1/2 e to the t minus 1/2 e to the minus t, both of which are in the table. Again, by the linearity property, Laplace transform of the difference, right? The difference is just this one plus minus this one, so both the differences too. Laplace transform of the difference is the difference of the Laplace transforms, and I can pull 1/2 out. E to the t and e to the minus t do have transforms in the table, right? E to the 1t is 1 over s minus 1, has transformed 1 over s minus 1. E to the minus 1t has transformed 1 over s minus the minus 1 over 1 over s plus 1. So I've just got 1/2 over s minus 1 minus 1/2 over s plus 1. And if you use your, if you put these over a common denominator with algebra, it's 1 over s squared minus 1 if you like. So there's the Laplace transform of sinh. It's 1 over s squared minus 1. Looks a lot like the transform of sine, actually, if you think about it. It was 1 over s squared plus 1 in that table. So transform of sinh and sine are so similar, maybe you want to memorize this one. I don't know. Some people do. Well, here's another one, sort of a lemma, I guess. You know what a lemma is? It's another name for a theorem that you prove on the way to proving some bigger theorem. If you want to call it kind of a stepping stone in a way, then you can call it, instead of calling it a theorem if you want, you can call it a lemma. So this lemma says if h of t is continuous in the interval from 0 to 1, and the integral from 0 to 1 of h of t, t to the n is 0, then h of t must be the zero function. The only function that you can put in here and get 0 is the zero function. And there's a short proof of it. I'm not going to go into a lot of detail on this. But it implies also then that this additional, with some additional stuff here, the inverse Laplace transform theorem, that if f of t and g of t are both of exponential order and piecewise continuous on every finite interval from 0 to a, then for some real number little a, the Laplace transform of f, a function of s, is equal to the Laplace transform of g, a function of s. For all s such that real part of s is greater than a, we can ignore that part. But it says that if two functions have the same transform, then they must be the same function, right? If it quacks like a duck and it walks like a duck, it must be a duck, right? Two functions with the same transform must come from the same function. In other words, there exists an inverse transform. If I'm given a function that is the transform of something, it has an inverse. It just has one inverse, right? One function that has that transform. So here's the proof of that. I'll leave that out for this class, but you can take a look at it if you want. And furthermore, it turns out that it's an integral in the complex plane, and so because it's an integral, it has the linearity property. The integral of the linear combination is the linear combination of integrals applies again. Inverse transform of alpha times a transform plus beta times another transform is alpha times the original function that has this transform plus beta times the function that has this transform. So it has that nice property too. That means you can find the inverse transforms. Suppose I say, here's a function that looks like the transform of something. I wonder what has that inverse transform. What has that transform? So I'll take the inverse transform. Well, the inverse transform of the sum is the sum of the inverse transforms by this linearity property. And what are these? I recognize these from the table. Inverse transforms are complex line integrals. They're too much for this class. What we'll do is we'll simply say, we'll look for these in the table to find the inverse transform. Right? So what had transform 1 over s cubed? That looks kind of familiar. wait a minute, 2 factorial over s cubed was the transform of t squared. If only I had a 2 factorial in there, right? Well, I'll put a 2 factorial inside and a 2 factorial outside to cancel it, right? Because we can do that, right? The constant can come out of here, you know, L inverse is an integral, and cancel 1/2. So this is actually equal to this. These two cancel each other. But 2 factorial over s cubed is the transform of t squared. So this must be the transform of 1/2 t squared. So that's what you do. You put a 2 factorial inside, 1 over 2 factorial outside, and then say this is the transform of t squared. So the inverse transform of t squared. Similarly over here, 1 over s plus 3, if I write it as 1 over s minus a negative 3, I recognize that's the transform of e to the minus 3t. And so from the table I get this back, table 2.11 here. There's how you do inverse transform. What's the inverse transform of 1 over s times s minus 1, I wonder? That's not in the table. Here's what you can do. You can use partial fractions. Remember partial fractions? We've been doing those. 1 over s times s minus 1 by partial fractions is 1 over s minus 1 minus 1 over s. Now, it's inverse transform of two things I do see in the table, right? The inverse transform of the difference is the difference of the inverse transforms. This in the table is the transform of e to the 1t, right? 1 over s minus 1 is the transform of e to the 1t. 1 over s, remember, was the transform of 1. So this is the transform of e to the t minus 1, even if you don't recognize it right away. All right, so for now, try some transforms. I give you some functions to take the transforms of, and try some and use the table particularly. Some of these, you want to take the Laplace transform of the sum and difference is the sum and difference of inverse transforms. Look up each of the 3 of these in the table. And then finally do some inverse transforms. How do you inverse transform each of these?